Yeah, so the next speaker is obviously a remote presentation, and it's from Clinton Roy, and the title is, H5pydantic. So please.
All right. Hello, everyone. My name's Clinton. I'm a software engineer at the Australian Synchrotron in Melbourne, Australia. The synchrotron is run by ANSTO, the Australian Nuclear Sciences Technology Organisation. The first 10 slides of this talk are synchrotron background and HDF5 background, so I'm going to zip through that, and as soon as I get to the guts of my talk, I'm going to slow way down. So we're going to talk a little bit about the Australian Synchrotron, a little bit about HDF5, and then the guts of the talk where I'm going to slow down is on a new library I'm working on, h5pydantic. This is a nice picture of the Australian Synchrotron on a sunny day. It is not sunny today. It is very rainy and windy and awful, so that hold on to that image if you ever visit. Our users would like simple user interfaces with one click of a button that does all of the paperwork, gets all of their funding, runs an experiment, analyzes the data, and writes a paper for them. My scientists that I work for are a little bit more forgiving. They would like all of the data and metadata of an experiment together. They would like the ability to handle bespoke sample environments, not necessarily easily, but they would like the ability to handle it, and they'd like to automate as much stuff as possible. These requests are far more possible for me to implement in one lifetime. And you know, I'm a support person, but I do have wants that I want. So I like to have a flexible storage format. So HDF5 fulfills that really nicely. And I don't see my role at the Australian Synchrotron as providing a finished user interface for my users or my scientists. I very much see my role as providing a toolkit of software bits and pieces that the scientists can plug together to get their experiments working, which means that I see myself as providing a toolkit that my scientists can tweak and improve on the code. And if they want to do weird, wacky experiments that we've never thought about before, they can do that. That also means that I want my beamlines that I'm working on to not have to rely on me, especially at 6 o'clock in the morning when things go wrong. As a personal thing, I don't particularly like working on GUIs. They're very detailed oriented. They require a lot of personal attributes that I do not have. There's a lot of patience. There's a lot of detailed oriented work. There's a lot of color stuff that totally goes over my head. So a lot of the time, if I'm forced to do GUI work, I want to generate the GUIs as much as possible. And in order to be able to generate that, I need a lot of information about my experiments, about my data storage, all in one place. So we're going to have a little hand wavy experiment slide. So you can think of this as a small, significant example of all of the bits and pieces that we store in an experiment. So we have the three main data types of numeric data types, and we are looking at sample data. We're looking at the raw data we're getting off of our instruments. We're looking at some of the calibration data, and then we've got a little bit of information about reduction processing. So this is my hand wavy HDF5 dump format that fits on a slide. So you can see here that we've got some sample information, we've got some X-ray beam information, we've got some calibration information, and we've got some processing information. To go forwards with this, we're only going to be looking at the calibration information. So the interesting stuff here is some of the harder aspects. We've got an array, as in we've got a no beam calibration image there, and we've got some integers, which are surprisingly hard to deal with in the way that I'd like to. So we're just going to be focusing on the calibration group there. So if you are wanting to get an experiment done really quickly, if you're wanting to get some code done really quickly, and you ask your software engineer to write something really quickly, they're going to do it by hand. So this is an example of writing out that calibration data We've run our experiment. Now we've got a bunch of events that have occurred, and we want to store those events in a HDF5 file so that we can later on go back and reduce the data based on this calibration information. So it's nice that I'm after the H5Py talk, because all of the work that I'm doing is building on top of that. So here we're making a group, we're making a data set, we're adding the data to it, and we're adding some attributes to it. Nothing at all fancy in here, but a lot of this code here is fairly generic, and it is amenable to being automatically generated in the future. So this is the point of the talk where I'll slow down, because this is where I'm introducing the library that I'm working on. So if you want to summarize this entire talk in one sentence, is that h5pydantic is a ORM, but instead of being an object relation mapper from models to a relational database, it's a mapper from models to HDF5 file. There's a big asterisk in that, because that's the goal of the library, and it doesn't really get all of the way there yet, or it does get all the way there, but with no bells and whistles. So if you're looking to map from models to a HDF5 file, in Python land, you've got a couple of choices about what libraries you use to describe your models. A very popular library to choose from is the Pydantic library. So the reason that my library is h5pydantic is it is a smushing of the Pydantic and HDF5 together. So that's probably all of the creativity I've used up for about 6 months coming up with that library name. So if we have a look at the smaller atomic types that we're interested in, and how we might map from the Python types to the HDF5 types, my main audience for this library is my scientists, and secondarily my software engineers in my team. I want to be able to describe eventually all parts of an experiment, all parts of calibration, all parts of raw data, and all parts of processing afterwards. So I want to do that in a way that is Pythonic as possible. So where possible, I want to use integer types. So it's really easy to map from Python bytes, Python strings, floats, lists, and NumPy arrays straight to HDF5 types. So in essence, there's really not too much work to do there. Python types, a lot of Python types map fairly cleanly to HDF5 types. The nice thing with a lot of Python types is that if you need to shuffle a little bit of extra data along with the Python type, it's often very easy to add an extra attribute to a Python object. Mostly when we're dealing with HDF5 stuff, we have a high-level type, but we also have to tell HDF5 what the underlying storage is. So, for example, with enums, we have to tell HDF5, do we want to store this as an int32 or an int64, etc. But that's really easy to do with Python, because we can just add in an extra attribute to a regular Python enum that tells HDF5 what underlying size to use. So if you remember back, I mentioned that integers are kind of a little bit hard and yucky. So Python doesn't really have fixed width integers as standard. If you have a number and you add, if it fits within a 32-bit number, and you add two of those together and it would go up to a 64-bit number, Python will do that for you, and it will just keep on going. That doesn't really work if you want to store things in a HDF5 file. You really kind of want to tell it exactly the size of those files. So I've had to come up with a couple of Pydantic types to describe fixed width fonts, fixed width integers for use with H5Pydantic. So there are a bunch more types to look at. So like tuples, for example, is one that I definitely want to look at. Complex types for complex numbers is one of the things that I want to provide a very standard way of doing it. There's a lot more work to do with these types, but the types that I have done so far capture a lot of information. So that's the low-level types. Then we go up a little bit and we want to look at how we want to model groups in Pydantic. So the way that we model a group in H5 Pydantic is with a Pydantic model. And I have labeled that, as I said, I've already used up all my creativity. So I've labeled that as H5 group. So that is a particular model that knows how to marshal everything that's put inside of it into a HDF5 file. Well, inside a HDF5 group, I should say. And the other major thing that we want to model is a data set. So a numpy array is the most likely form of a data set, but I also want to make it really easy for our use case where we have detectors that generate lots of TIFF files, for example, and I want to be able to say, create this HDF5 data set from this TIFF file. I want to make that as easy as possible because that's a very common thing as well. So those are the three sort of mappings that we've got. We've got our lowercase, our lowest common denominator types, our atomic types, and most of those map to HDF5 types with a little bit of squishing at times and a fair bit of squinting when you have a look at integers. And then we've got two Pydantic models for modeling groups and data sets. So now let's have a little look at the actual library itself. Sorry, we've got attributes as well. Attributes work really nicely as fields of the models. So it's really easy just to add in extra attributes to any of our groups or any of our data sets. So I've got a few overall goals of H5 Pydantic. I want to make it easy to use and hard to get wrong. So if you can instantiate a H5 Pydantic model, you must be able to save that to a HDF5 file. If there's any sort of error marshalling any of the values of your instantiated module into a HDF5 file, that means that one of the validators I've written to make sure that all the numbers are fitting in the right size, to make sure that all of the strings are fitting in the right size, has failed. And that's a bug in H5 Pydantic. I don't want to hide the fact that I'm using HDF5 underneath, and I want to make sure that it's really easy to get at the HDF5 files underneath in case you need to do anything funky. And I also want to make it easy to use all the H5 Pydantic features as well. So I'm not trying to be a library that hides underlying details at all. I'm just trying to be a library that gives you access to all of the underlying details. So if we go back to our calibration example, this is a basic example of how we might use the H5 Pydantic library. So we sort of have to, it can be easy to read these from the bottom up. So at the bottom, we've got an experiment and we're only doing the calibration. So we have a group and that has a field of the calibration type. The next up, we have a calibration and that is a subclass of a group again. So it's another group. So you can see how easy it is to get a nested group. We've got the position, which is our XY class, and we've got our no beam calibration image. And a calibration image is a subclass of a data set. So that's storing an array. And as well as being that, we also have the extra options where we tell H5 Pydantic that the underlying storage type is a 32-bit integer and the shape is a 3-2 array. And then we have the position as well. And you'll notice that I've got those fixed width integer types. You declare the types as those fixed width integer types, but you use standard Python integers. You don't need to instantiate any special types there. So if we've got that calibration set of models, and there's a little bit of wordplay going on where what we've actually got is a set of models, but overall we call it one model. So if we have done a calibration run, for example, and we want to dump that information to a HDF5 file, we instantiate an experiment, and that experiment's got a calibration and it's got all of the underlying things here. So you can see here that although we've got the X and Y of position as being a 32-bit integers, we just use regular integers to store the values, and it's up to the validators there to make sure that those integers are within that range. If they fall outside that range, position will fail to instantiate and stop you from getting to a point in time where you have a structure that you can't dump. And you see here that for the calibration image, we instantiate it from an array. And similarly, you can instantiate it from a file, for example. So if you've got an image file that your detector creates, you can instantiate the calibration image model from that, which is a very standard thing to do. So once you've done that, then it's an easy process to dump that h5pydantic models into a HDF5 file with the dump. And later on, if you're working with that data, you can fairly easily load it up. You load up your experiment model, and then as a instantiation, you load up the same experiment HDF5 file that you previously dumped. You use the load, and then you can get the elements underneath it. So that's a fairly simple overview, but also a fairly comprehensive overview of how I want all experiments at the Australian Synchrotron to be configured. I don't want us to have to sit there and handwrite a lot of H5 code. I want us to be able to declare the structures, and I want us to be able to add in any funky code that we need to on top of that. But I don't want us to make it hard for our scientists to add new bits and pieces to their experiments. So Pydantic itself can be much more expressive than what I've shown. It can show you can express much more than just a simple type in the models. You can add as many fields as you like. So documentation, extra validation, which I'll have an example of. You can add in unit information, and you can have relationships between fields and a whole host of other things as well. So as a bit of a richer example of some of the things that you can do with h5pydantic, and well, these things come from Pydantic. It's just that the models that I give you let you dump that in a HDF5 file in a reasonably useful way. So here we've got a group model describing a couple of features of your beam. So we've got an energy, and we are declaring that to be a floating point number. It's got to be greater than or equal to 0, which seems like a fairly reasonable validation. We've got a little bit of documentation there describing what this energy field means. And we explicitly say that this particular field has a unit of an electron volt. And the next one that we've got there is another sort of calibration field where we are describing the distance. So we are describing with a little bit of documentation, again, the distance has to be greater than 0. We have got a little bit of documentation there saying that it's got to be the distance from the sample to the detector. And we've got a unit there of being a millimeter. So you can sort of see that if you were to start describing your experiments, your beamline, with that level of detail, and obviously more levels of detail, you would get a set of Pydantic models that really, really well explain your beamline setup and your experiment setup. And the hope is that if I've got enough information here describing all of that, then later on I can essentially automatically generate the code required to take all of the outputs from an experiment into the HDF5 file. So with that documentation, HDF5, you can do things with Sphinx, for example, where if you have a Pydantic model and it's got extra features like documentation and units and types and things like that, you can generate a PDF file with all of that information contained in it so that you've got documentation for your set of models. So you could hand someone a HDF5 file and you could hand them a PDF file, which describes all of the keys in the groups and all of the attributes in great documentation and great detail. You can also start to do versioning, because we can store version fields inside the models ourselves, and we can export that into the HDF5. And when you load it up, you can know that you've loaded up model 123 of the model, and you can check that the documentation you're looking at is the right version. So moving forward, I want to use the library much more. I've done h5pydantic sort of in between doing my day job, and other beamlines at the synchrotron have started using it. I have not used it on my own beamline, so it's the classic plumber's problem there. So I definitely have a lot of features to add to it so that we can use it in everyday experiments, but we are getting there. Most of the examples that I've done here are on version 2 of Pydantic, and that's in a branch at the moment. I haven't made a release with that version yet, but that's going to be happening very shortly. And I want to integrate with more tools. I want to integrate in a tighter way with Pynt. It should be possible to get Pynt to check more typing stuff that I'm doing. So Pynt will let you do mathematical expressions, and it will check that the units of the individual parts of your expression have the right types. So it makes it so that you can't do mathematical operations between different expressions that have the wrong types. I can't make use of that with the way that I've done it in h5pydantic, but I definitely want to. And I want to be able to integrate with syncs more as well. The way that I've got things set up at the moment means that it's really easy to instantiate the entire model and dump the entire model. Obviously, one of the things you want to do is be able to just load up parts of the model. In particular, while an experiment is undergoing, you have an array of image data. You get one more image, and you just want to load up just that image data and just append that new image and then put it back, rather than loading up the entire model. And I've got some work done in that, but I think it needs more work. We use Blue Sky a lot at the Australian Synchrotron. It is an orchestration technique built on top of OFID, which is built on top of EPIX. Essentially, when we run an experiment, we get a whole bag of network events, so that every sensor, every motor, every valve and gate and thing that we move around, we get a whole bunch of information about what sensor this information came from and what's happened. So the temperature's increased, or this motor's moved from this position to that position. And what I would love to be able to do is take the models that describe all of our beamlines and tag them with a OFID event source, and then do a reverse mapping of that. So create an index file so that we index our models that describe our beamlines via the OFID sources, and then be able to, as these blue sky events are coming out of an experiment, use that index to work out where they belong in the HDF5 file and automatically generate our aggregator. That's my main goal that I'm working towards. And I also want to be able to accept blue sky events without having to have a backing model. So the current beamline that I'm on at the moment, we've got something like 50 temperature sensors. I should not have to put all of those individual temperature sensors into my model. I should just be able to have a temperature sensor, and anytime our aggregator gets a blue sky event that says it's from a temperature sensor, it should just go somewhere in the HDF document. And as long as they're nicely individually named, I don't really care. And a really big goal is, once an experiment has generated a HDF5 file, in 12 months' time, maybe the user wants to come back and they want to rerun their experiment with a slightly tweaked example or a slightly tweaked sample, for example, or they want to do something slightly differently. I want to be able to take the HDF5 file from their previous experiment and set up the beamline in exactly the same way and then let them tweak things. So I see the HDF5 file as a really powerful format to describe everything that happens to a user through their experimental run. There's all sorts of weird and wacky ideas that I've had during my moments of inability to sleep. So one of the things that I thought of is putting the entire Pydantic model within the HDF5 file itself, such that if they install h5pydantic, it would have a method to extract the JSON form of the Pydantic models from the HDF5 file. And then in the HDF5 file, we'd have all of the data, metadata of the experiment, plus all of the code that lets them explore that as a model. I'm not sure if that makes sense, but it is the thing that I have been thinking about. I would like to thank the scientists on the beamline that I spend the most time on, Dr. Andrew Clulo, Dr. Anne-Marie Warrender, and Dr. Leslie Barntley. They let me do these little side projects that eventually lots of people at all of the beamlines get to use in between doing my real job, which is handwriting some of this code. And I'd like to thank everyone who's already given feedback on the library. And thank you very much.
Okay, thanks a lot. Yeah, question in the back.
Yeah, hi, Shandor Brockhauser. A quick question. As far as I understand, when you're building your Pydantic model, you can actually also add documentation, but this is something which you do manually. You just basically type the things in, and what your aim is for the future, that if you have already typed in something, then you are basically make a class which you can then reuse later, so you don't have to type it again. Now the question is, if someone has already typed things in, for example, in the Nexus standard, we've got already lots of documentations for sensors, for everything like this, exactly the things you also mentioned. Have you imagined that you are making a converter? So basically you can build your Pydantic model from Nexus base classes?
Yeah, so we definitely want to reuse as many standards as possible. One of the nice things with HD5 is that it's a very generic file format. So we are describing lots and lots of things that are not outcomes, typical outcomes in experiments, but definitely when it is possible to reuse existing standards and existing documentations and things, I definitely want to do that. Absolutely.
Perfect. Thank you.
And there's another question in the room.
Hello. Thanks. Yeah, that looks really nice. Just a kind of very specific question is your like integer specific width definitions. Would it be practical at all to use like NumPy's, you know, in place of your own types for annotations? Would it be practical to use like, you know, NumPy int32 or whatever as the annotation there?
Yes. So the only thing that I've looked at the moment is that I need something that h5pydantic I can add get validators for. So at the moment, I'm using my own types, but I can certainly go to other types. And I've had some thoughts that maybe I want to do some of this by policy. So like maybe I want to say in this class, whenever we say an int, we mean an int32, but in this class, whenever we say an int, we mean an int64. But at this point in time, I'm just being very explicit, which is a Pythonic thing. And just because I'm using my own int32 class does not mean that I can't use another int32 class in the future.
Okay, thanks.
Okay, thanks a lot. I think we're going to need to move on to the next talk already, but let's thank the speaker again.